Alright everyone, welcome back to Ham Radio Technician Class License Preparation. This is number 4, going through some stuff that's a little better, a little more theory along the lines of propagation and antennas. And by the way, quick note, this will start to get a little more fun and exciting, and that's will dry. Once we get up to number 7, I'm going to do some short video clips in with the questions to help with the understanding of the answers and so on. And make it a little more educational besides just studying for the test. Alright, so our first question here is, why are UHF signals often more effective from inside buildings than VHF signals? And the short of that is because the wavelength is shorter as you go up in frequencies, this allows the radio waves to more easily penetrate the structure of buildings, or, well, structure of buildings really, because we're talking about from inside buildings. So that's the reason for that. As far as the other answers, VHF signals lose power faster over distance. Well, I don't think so. That not necessarily any more than UHF would, because it just follows an inverse square law anyway for electromagnetic fields. So it's the same regardless of the frequency. And C says this is incorrect. VHF works better than VHF. No, I don't think so. And UHF antennas are more efficient than VHF. Well, if you got a handheld inside of a building with a rubber duck, well, you know, then that's not even going to be an issue really as far as comparing antennas. Alright, so next question is, what antenna polarization is normally used for long distance weak signals, CW, which is Morse code, and SSB signals, sideband, using VHF and UHF bands? And the answer is horizontal. It's not a hard, fast rule, but it's a common practice for the antenna to be horizontally polarized, meaning that it's like, if you remember the old-fashioned TV antennas, the way they were facing, or like if you're laying down in your bed, you're horizontal that way. That orientation is typical, and then vertical is more like what the repeaters use. If you had a handheld and the antenna's pointing straight up and down, that's vertical. So that's the polarization or polarity of the antenna. And there can be a substantial loss of signal between horizontal and vertical polarity, as much as 20, well actually as much as 30 dB. I would say a minimum of 20 dB. And that's could make the difference between hearing somebody and not hearing somebody. 30 dB definitely can make a difference. 30 dB is like 5 S units on a properly calibrated meter. So if somebody was, say, S9 and you had a noise floor of S4, and they switched polarities on their antenna, if they could, or switched to an antenna that had the other opposite polarity, they could end up in the noise and you may not even hear them or not hear them well. So it does make a difference. Could make or break a contact. Okay, next question is, what can happen if the antennas are opposite ends? Okay, I just talked about that. And the answer is signals will be significantly weaker. It's just asking about polarization and what happens if they're the opposite. And I've already addressed that issue, actually. Didn't realize that was going to be the next question. Okay, this one says, when using a directional antenna like a Yagi or a beam, a lot of the CBers and hams both call them beams, but they're Yagis, I guess, technically. How might your station be able to access a distant repeater if buildings or obstructions are blocking the direct line of sight path? And the answer is, well, it wouldn't be switched from vertical to horizontal. That would not be good because, like I said, you can get a lot of loss of signal that way. That would not help your case. B is try to, and that's the answer, try to find a path that reflects signals to the repeaters. Sometimes that can happen. I've done that actually before when I lived near a mountain. I actually pointed my antenna at the mountain and got more of a signal bouncing off the mountain than I was, doing it a different way. There's also a thing called knife edge refraction, where you can point your antenna at the top edge of the mountain and it'll actually bend the radio waves as it goes over the top. I've seen that happen. I've seen it work, but I don't really know all the specifics on that one. And increase the antenna SWR, that's just probably not a good plan no matter how you do it. That's a topic for another set of questions. Okay, next question. What term is commonly used to describe rapid fluttering sound sometimes heard when mobile stations are moving while transmitting? It's called picket fencing. And the only way I can think of to remember that is, if you think of, if you had like a picket fence, with the pointy tops on them out in the yard, and you took like a drumstick or just a branch, whatever, and walked along the fence tapping on the top things as you went by, kind of like just running and having to go tick, 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 tick across the fence. That's kind of picket fencing, what it sounds like almost. If it's bad enough, you won't understand what the person's saying. If it's just light picket fencing, you're probably still, your brain tends to fill stuff in sometimes. Next question. Sorry, I have the sniffles here. I have a headache as well. Trying to get a couple of these done for you guys. Try to keep the audience happy, as they say. What type of wave carries radio signals between transmitting and receiving stations? It's kind of a memory thing unless you know electronics enough to know, but it's always electromagnetic. Okay, I mean, anytime you put an electric current through a conductor, which you're doing when you send a RF signal to an antenna, it creates or induces a magnetic field. So that's why it's electromagnetic. Okay, any other answer is wrong. Which of the following is likely a cause of irregular fading of signals received by ionospheric reflection? The answer, this is kind of more of a memory, I guess. Random combining of signals arriving via different paths. I have an interesting little story on that. When I first got my license, back when they had novice licenses, and I was on Morse code, or CW, and I was listening to a station. He was kind of weak, but I could actually hear an echo on his signal. So when he was doing Morse code, you hear like da 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 da, and it's hard to make that sound right. But the second version of it was lighter and weaker than the first version. And I was actually, what was going on is I was actually hearing his signal going from his station to me, direct in the sense of maybe bouncing off the ionosphere, but the shorter path to me, I guess would be a better way to put it. And then I also heard his signal going all the way around the world, long path to me, like a 1/7 of a second or so later. So I had like an echo to it. So it's kind of interesting. So again, that can happen, and in the case of fading of signals, the same thing. I guess in our case, though, for a technician, you'd be more dealing with just actual reflections of different types, including ionospheric reflection. I mean, especially if you're mobile, you can get some weird stuff that way. Next question, which of the following results from the fact that skip signals refracted from the ionosphere are elliptically polarized? I guess they're saying, this is a new question, I don't think I remember this one from before, that either vertically or horizontally polarized antennas may be used for reception or transmission. I guess just due to the way that the signal has become polarized during all the refraction. And by the way, if you look if you bounce a flashlight beam or laser or whatever off of a mirror, that's reflection, okay? Or if you see your image, that's reflection, okay? Because that's an exact thing where the angle of incident equals the angle of reflection, whereas refraction is a bending of a signal or a wave or whatever. So it's not exactly the same as reflection. So you guys might want to reflect on that. That cracked me up. All right. Next one. What may occur if data signals propagate over multiple paths? The answer is, oh, and it's data signals too. That's important to differentiate there. And the answer is error rates are likely to increase because data is kind of picky about how it's sent and received, and well, how it's received actually. And if there's any distortion or shifting due to paths like that, it'll definitely increase the error rate a lot actually. It's not, I don't know that I've ever really seen it that much, but it could happen, and I guess that's their point. Next question is, which part of the atmosphere enables the propagation of radio signals around the world? It is the ionosphere. It is always the ionosphere. It always will be. How to remember that? I don't know. Maybe, I was going to say think of a car like an ion, but you can't because there's also a stratus. So, and there's a stratosphere, so you can't do that. I guess you'll just have to find a way to remember ionosphere. Okay, then we're in the next group. Next group is radio and electromagnetic wave properties. Oh, so what is the name for the distance a radio wave travels during one complete cycle? And that's a wavelength. We talked about that on one of the earlier videos. So our next question here is, what property of a radio wave is used to describe its polarization? And it's the orientation of the electric field. It's interesting because there is an electric field and a magnetic field, and you know, when you induce a current, RF current on the antenna, it creates an electromagnetic field. But yet, when it comes to polarization, they talk about the electric field. Find that interesting. Next question. What are the two components of a radio wave? Yeah, I just said that, didn't I? Electric and magnetic fields. Ha! Getting ahead of myself here. Next one is, a lot of these are memorization, again. So, and there's no real reason to be able to explain, or how I would explain some of the wrong answers in these cases. So next question, how fast does a radio wave travel through free space? It is always at the speed of light, always and forever. If you think about it, it makes sense because lasers, lights, flashlights, so on, those are frequencies as well. They're just really high frequencies. So they travel the same speed as radio waves do, and conversely. So then radio waves travel at the speed of light. Okay, so I mean that's kind of a way to remember it. How does the wavelength of a radio wave relate to its frequency? We've discussed that before, but again, the wavelength gets shorter as the frequency increases. That's just something that you do need to remember, and again, it kind of relates to resonant frequency. We talked about that, and bigger and smaller tuning forks. The smaller tuner forks would have a higher frequency, that kind of thing. What is the formula for converting frequency to the approximate wavelength in meters? The answer is D, the wavelength, in this case, wavelength in meters equals 300 divided by the frequency megahertz. That's the same exact formula that we used. Now, be careful here. I just noticed this, and if this is like this on the actual test, it could trick you. Because it also has wavelength in meters equals, well, maybe not, It has, but it has in hertz, and it has 300. Okay, and if it said wavelength in meters equals 300 divided by the frequency in hertz, that would be wrong. Okay, the reason that it works at its megahertz is because the actual speed of light is 300 million meters per second. I had to think about that. So in that number, 300 million, if you go back to just the number 300, there's 6 zeros, okay? And in megahertz, there's 6 zeros. So when you're doing a division like that, when you're dividing 300 million by, say, 146 million, you can drop the 6 zeros off of both sides, and it would be 300 divided by the frequency in megahertz. That's why that works, in case anybody was interested in why that works. Next question, what property of radio waves is often used to identify the different frequency bands? Which we know is the approximate wavelength. Again, that's not an exact science, so you do kind of have to remember the bands and the, like 50 megahertz to 6 meters, that kind of thing. At least get you in the ballpark. And then if you have the formulas, you can do the math as well. Next question, what are the frequency limits of the VHF spectrum? Okay, on these, there's a pattern. There's several questions that are like this. There's HF, UHF, VHF. Okay, the reason that they're giving you these also, by the way, is because your frequencies, your main frequencies for technician class is you get 10 meters, which is HF in the HF band or spectrum. And then you have some in the UHF spectrum and some in the VHF spectrum. The pattern I want you to see is these are all like 3 to 30, 30 to 300, 300 to 3000. Okay, it's always got 3's and 0's. So anything other than that, it's going to be wrong anyway. And so I'm going down here to HF. HF is 3 to 30. Okay. It actually goes like this, just so you know. It goes LF, which is low frequency. There's stuff below that too, but I don't care. And then there's HF, and then VHF, and then UHF. So VHF is very high frequency. UHF is ultra high frequency. And then, of course, HF is high frequency. So you can kind of see they go in order. HF, VHF, UHF. So HF is 3 to 30. The next jump then would be logically 30, because you have to start where you stopped here, 30, and then add a 0, 300, and then the next one up, oops, I went to the wrong one. They had these out of order. Up here it would have been 30 to 300 for the next one, and then you add another 0, and it's 300 to 3000. Okay, and it's always megahertz in the case of the way they've got this, and I'm sure the way it's on the test is going to be the same thing. And there's frequency spectrum charts out there you can look at. And like I said, again, there's band plans out there. That's important to view through those two. Okay, last one. What is the approximate velocity of a radio wave as it travels through free space? We've already talked about that. So it's, oh, now this is a little bit of a trick question here. It's 300 million meters per second, which is also equal to 186,000 miles per second. Not per hour, okay, per second. So don't let this throw you. Okay, and if they're giving this as the right answer in the question pool, then I would say most likely that just look for the 300 million number, and the rest of it here is probably going to be right anyway, but you don't know. So just keep it in mind that either one of these numbers is per second, whether it's miles per second or meters per second. Okay, that's all I got for these for number 4. That should be close to 15 minutes. So thanks for watching, appreciate it. Any comments, put them in the bottom. If you want me to go over any of these questions in more detail, let me know that too. Okay, I'm here for you guys, and I want to give you as much information and the best information I can so that you're able to pass the test. And by the way, while you're going through these and I'm doing these, it doesn't hurt to go out and play on the site with like the flashcards or whatever, and or practice test if you prefer, but I would wait for a while for that. But you can, it's not going to hurt to kind of get used to how the questions are worded. And if you do the flashcards, you can actually learn and memorize a bit of it that way, just using those. So that can be productive as well. Anyway, thanks for watching, and we'll see you at the next one. 7-3 for now.